So this lecture is about Hermite interpolation. We're going to take a few more things into consideration when we interpolate our functions. The idea is that we want to create a polynomial that agrees with the function's value and its derivatives at a set of points x0 through xn. And so we have our data given, say for our value x, and then the value y. The function assumes the derivative of the function, the second derivative, up to a certain number of derivatives, and for the different points that we have under consideration. And it could be that we don't have all of this data, but if we have the value at any derivative, we'll have all of the values below that derivative. If we have it at at y double prime, we'll have it at y prime, we'll have it at y, all the way down to the base. Okay, and so let's look at an example of how we might do this. I am going to do the sine of pi x, and the derivative of the sine of pi x is pi cosine of pi x. And my data here at -1, the function is 0 and its derivative is equal to -pi. At 0, the value of the function is 0 and the value of the derivative is pi. And at 1, the value of the function is 0 and the value is -pi. Value of the derivative is -pi. So I do my table a bit differently. I'll put in the top line will take the data, okay. But then since it's one derivative, I'll put in a line with just the value and without the derivative value just below that. And then same here for the value at 0. Okay, I put in 0, 0, pi, and then again, since I have derivative, leave a blank here. And again for my last data, and then below that, okay, just put in an asterisk. I'm not going to fill that in. Then I go through the divided difference process exactly as before. Okay, and when I do, it will give me coefficients of my polynomial like so. And I can put these into my polynomial, and so here, right here is my interpolating polynomial for my sine function, for sine of pi x. I can graph both of these. The blue one is the original function. The orange one is my interpolating polynomial. Notice it's a little bit off at like 0.5, okay, and at -0.5, but it's just pretty tight everywhere else. Okay, here I have another example for no particular function, but I just have the data. But notice here I have it to the second derivative, and again, if I have a second derivative, I have to have all of these values above it. If I had a third derivative, I would have so forth. So this, if any number of derivatives I have to fill in all the way above this. Okay, now I put it in here, and notice I'm being a little bit more careful here, because we can't just put in the value of the y prime. We're putting in the value of the y prime divided by 1 factorial, which is 1. That's why it didn't show up in the first one. But when we go down here, and I have the value of the first derivative and the second derivative, then I put in 7 divided by 1 factorial, and this should be a 6 here. Okay, that needs to be fixed. I'll mark that in red. That needs to be fixed to be a 6 divided by 2 factorial. Okay, and so the factorial, what you factorial, is the number of derivatives. If I were to go out to 3 factorial, it'll be divided by 3 factorial. And a way to remember this is, if we're just having the data for one point, my interpolating polynomial is going to be the Taylor's polynomial. Okay, so this Hermite polynomial, Hermite interpolation, is a way to generalize the Taylor polynomial. Okay, I'm going to find the Hermite polynomial by divided difference using the same data as in our last example. I'm of the opinion that seeing somebody's hands do it actually helps. Okay, so we take our data here. The first line, I'll have 1, 2, 3, and notice how I've written my derivatives out along the top. I'm of the opinion that this will help you think about it as like a Taylor polynomial, and that will help you remember a lot of the things that you need to do. Now, since I have including one derivative here, I'm going to have to use one extra line. Okay, then this next one goes 2, 6, 7, and then 8 divided by 2 factorial. 2 factorial is 2, so 8 divided by 2 is 4 there. And since I used 2 derivatives on this, I'm going to have to put in 2 extra lines. Okay, and so let's see, I'm going to have to be filling in the rest of this, and I've done this a few times, so I know we're going to stop here at the fourth term, but anyway, we will need this in order to calculate this. I need a number here. To calculate this number, I'll take the difference between these. Okay, so I go 6 minus 2 over 2, 2 minus 1. And so this 2 goes with this 1 right here. And then since we're in the first calculating column, we just have one step between the two things here. And so this gives me 4 over 1, and so I'm putting in a 4 here. One thing I want you that I think is cool is that this is our actual derivative here. If we think back on calculating it, well, it looks ridiculous, 2 minus 2 over 1 minus 1, but if we think of this value as an f of x plus h, and this one is an f of x, and in the denominator that one as an x plus h, and that one as an x, then hey, it gives us the derivative at that point. Anyway, I think that's a cool way to think about it. All right. And so we've gotten all we're going to get from the first column. Let's go over here, and we have all we need to calculate this point. Well, okay, so we'll do 4 minus 3. Okay, that 3 corresponds to this 1. But since we've moved over a column, we need some space between the things in our denominator. So I go from here to here. So that 1, this 1, okay, but that's a 2, so 2 minus 1, so this will be 1 over 1, and so I will have a 1 here. Okay, now I need to calculate this. Well, okay, that 4, 7, so 7 minus 4, and this 1, and then a 2 minus 1, 2 minus 1, and so this will be 3 over 1, which will put me a 3 here. Okay, so I need that number right there. Okay, so it's 3 minus 1. Okay, this is, I'll put this one in the denominator, but I need to skip up 2. So 1, 2, so I'll have 2 minus 1, so this is 2 over 1, so that's a 2. And so this number right here, that'll be 4 minus 3, and the denominator will be 2 minus 1 again. And so this is 1 over 1, and so this is the number 1. And now I'm here, okay. Get myself a little more room to work with. What will I have? Let's see, I'll do a 1 minus 2. And the denominator, well, again, a 1 in the bottom here, but this time I skip 3. So 2 minus 1, and so this is a negative 1 over 1, and so I have a negative 1 here. And so let's roll it all together. Okay, my polynomial is equal to 2 plus 3 times x minus 1 plus 1 times x minus 1 squared plus 2 times x minus 1 squared times x minus 2, and then minus x minus 1 squared x minus 2 squared. And so there we have it, and that's just hunky-dory because it matched what I've done working it the 3 other times that I worked it.